In this video, we're going to take a Laplace transform of this second order model that we developed for our mass spring system. Now, in order to take the Laplace transform of both sides, we'll have to take the Laplace transform of the second derivative term and the first derivative term. And I'll be using these relations that can be looked up in your textbook on how to take the Laplace transform of first derivative, second derivatives up till the nth order derivative. And remember that the initial conditions that we were playing with, we said that at time t equals 0, our x value was 0, and at time t equals 0, our first derivative was also equal to 0. Once we incorporate these initial conditions into the Laplace transform, this term and these two terms go away. So the Laplace transform of our differential equation. So let me write that down once again. Okay, so we have the left hand side and the right hand side. And we're going to take advantage of the fact that the Laplace transform is a linear operation, which means that I'll pull out all the constants and just take Laplace transform of the time dependent terms, which include the derivatives. So tau square comes out, 2 times eta and tau also comes out. Laplace transform of x, and k is also, the gain of the process is also constant, so that also drops out of the operator. Alright, so using the relations for the Laplace transforms of our derivative terms, we'll be left with tau square times s squared capital X of s plus 2 eta tau s of s times x of s, and for the x term, it's just the Laplace transform is just going to be x. Now for the Laplace transform of the forcing function, we're dealing with the most general case. We don't know the exact functional relationship between f and time, so we're just gonna assume that the Laplace transform of f of t just spits out the following result, f of s. Just the most general case. Okay, alright, so now on the left hand side, if we factor out x of s, we're left with tau squared times s squared plus 2 eta tau s plus 1, and on the right hand side I obviously have k times f of s. Dividing both sides by this second order polynomial, we're left with x on the left hand side and k divided by the polynomial on the right hand side. Okay, now if you want to analyze the stability of this system, you'll be taking the roots of this polynomial. For higher order systems, the Laplace transform becomes more and more useful. The higher the degree of this the higher the degree of your system, the more the more advantage you can take of. So roots of this equation, if the real parts of your roots are, so a second order polynomial is going to have two roots. If the roots are complex, you get an oscillatory response. If the roots are, if the real parts of the roots, I'm gonna call that the real part of the roots is greater than 0, then your system is unstable. It's gonna be exponentially growing. If the real parts of the roots is negative, then your system is stable. It's gonna decay down or reach a final steady state value. And if I represent this final equation as x of s divided by f of s equals k over tau square s squared plus 2 eta tau, oops, I was missing a tau term here, s plus 1. This, ladies and gentlemen, right here is what we have we have obtained the transfer function. This expression right here represents the transfer function of the variable x with respect to the variable f. Okay, and a transfer function is one of the most important tools used in control theory because captures and communicates uh, it captures and communicates all the essential information that is required to study the dynamic behavior of a system. It captures how aggressive slash sensitive the process is, and as we discussed earlier, the roots of the denominator, the zeros of the denominator polynomial term, tell you whether your behavior is oscillatory, stable, or unstable. So in the next videos we're gonna move forward our discussion by looking at transfer functions in detail. Alright, I hope this video was helpful, and I'll see you next time.